Hello, in this video I'm going to go over hydrolysis reactions and how we've applied those in class so far. So hydro, water, lysis, split. Hydrolysis means to be split by water, and this applies to three different functional groups that we have discussed in class so far. So we'll start with the first one, which is the amide group. With the amide, we have a carbonyl, C double bond O, and that is adjacent to a nitrogen. And in the case of peptide bonds, that nitrogen is going to have one hydrogen attached to it. So whenever an amide reacts with water, it is going to split that amide up, and it will split right here. So that is the reaction point. That's the bond that gets broken by the water. And what we end up with in the end are two separate compounds. We end up with a carboxylic acid and an amine. So we're basically adding H2O. We've added HO, now we need to add the other H. And in this case it will be two hydrogens. In reality, we know that if the pH is low enough to protonate this carboxylic acid, there will also be an additional hydrogen on this amine. So in reality, what's really going to happen at a pH of, say, 7 is both of these are going to change. This is going to be a carboxylate ion, and the amine will be in an H3 group. So at a physiological pH, this is what will exist, and this will of course be positively charged to balance out that negative charge. So we see here that these are two separate molecules. We got an amide that was hydrolyzed by water to form a carboxylate ion and an amine. Okay, so that was the amide group. Next is the ester, and the ester, as we know, is in many different biomolecules. In particular, we've seen it in fatty acids, or I guess in triglycerides. But really any ester can be hydrolyzed, any ester can be, water can add to it and break the bond, and the bond that will break with an ester is going to be this one right here, the one that is next to the carbonyl and this oxygen that's bonded to two carbons. So this would be like an ether. So an ether plus a carbonyl is going to make an ester. And the bond that breaks is the one that's in between the two. And it will again split it into two distinct molecules. What we get with this is a carboxylic acid and an alcohol. Here's the carboxylic acid and then the alcohol. Okay, so if you split an ester with water, an ester that's hydrolyzed results in a carboxylic acid and an alcohol. And the third one is a glycosidic bond. This happens with polysaccharides and disaccharides, I guess oligosaccharides and polysaccharides. Anytime there are multiple monosaccharides bonded together, they are linked through a glycosidic linkage, which is really an ether linkage. This can be hydrolyzed as well, and this will actually result in two alcohols. So what we'll end up with is the bond that breaks, it doesn't really matter which one, it's either this one or this one. It doesn't really matter. This oxygen is going to go with one or the other of the monosaccharides. So it's not like both bonds are breaking. It's only one of the bonds that breaks. It doesn't matter which one you choose. What we end up with in the end is an alcohol group here, plus a mirror image. Of course, depending on the type of saccharide it is, will depend on what the product really is. But the point is there are two alcohol groups now present, whereas here this was an ether linkage. So the way that monosaccharides come together is through dehydration where water is released, and the way that they break apart, the way that they're hydrolyzed and digested is through hydrolysis, and they're broken apart into 2 separate monosaccharides. Okay, I hope that was helpful. See you next time.